Yes, I work in experimental particle physics, and specifically I work on neutrinos. Uh, Neutrinos are particles which are notorious for being almost impossible to detect because of their weakly interacting nature. And neutrino also exhibit interesting phenomena called flavor oscillation, where a neutrino from one flavor can transform to another one as it travels. Precise measurement of this flavor oscillation tells us about the properties of neutrino, and it can also shed light on important questions in physics, such as the mechanism with which mass is generated and the matter antimatter asymmetry that we observe in the universe. My thesis work focused on the experiment DUNE, which is a future neutrino oscillation experiment under construction in US. So DUNE is a long baseline neutrino oscillation experiment using an accelerator based neutrino source, which means that we produce our own beam of neutrinos so that we have a highest intensity possible and a very well characterized beam. Then DUNE will also have a near detector which is placed very close to the source, so we can precisely measure the unoscillated beam flux. And then we will let the beam travel 1300 kilometers before we observe it again at the oscillation maxima, so we can measure this oscillation with maximum sensitivity. And my work was focused on the prototype for the far detector of DUNE, which is called ProtoDUNE at CERN. And I looked at the beam data to understand, do these detectors reconstruct particle interaction well? And I also worked on how can we efficiently detect the light that is produced when particles deposit energy in argon. And this light is produced in deep ultraviolet, so we also have to first convert it to visible regime before we can see it with photosensors. With the ProtoDUNE data, we also saw that the modeling needs to be slightly better because there's still some mismatch between simulation and data. On the other side, I also worked on light detection studies, where I first demonstrated that a commercially available polymer known as polyethylene naphthalate is a viable and stable wavelength shifter in liquid argon, so we can see this UV light. We also built a new experimental setup at Nikhef, which we call Vulcan. This setup allows us to measure the optical properties in the UV regime for the detector components, so we can precisely understand how the light propagates in the detector. So this work will feed into the analysis that will come later. Pion-argon interactions with multiple pion final state was never measured before, so it was a very important input to the simulation to confirm that we are not biasing our modeling of these interactions. So this will be useful to make sure that we really understand our physics and we do not bias our measurements. And lastly, the setup at Vulcan. The optical properties of material vary quite a bit based on how they're produced, how they're stored. So this means that if we do not really understand them before building this detector, we do not know exactly what light will do in the detector. Really important facility, so we can understand all the components that we put inside the detector. We can select them before building the detector to maximize this detection of the light. So I hope that from this people can learn what I investigated and then expand it further to improving the algorithms.